Nowadays, the entire world runs on electricity. Lights, fans, air conditioners, mobile phones, music systems, computers, factories, hospitals, data centers, even modern vehicles. Everything depends on it. And the moment electricity disappears, life as we know it freezes instantly, which alone proves how deeply electricity is woven into human civilization. Yet, despite using it every second, most people don't really understand what electricity actually is, how current flows, what voltage means, or how a bulb turns on the exact instant we flip a switch. So before diving into complex formulas and confusing terms, the simplest way to understand electricity is to go back to the smallest building block of matter itself, the atom. Atoms are unimaginably tiny, invisible even under powerful microscopes, but inside every atom lies the entire story of electricity, with a dense center called the nucleus, made of positively charged protons and neutral neutrons, while negatively charged electrons move around this nucleus in regions called shells or energy levels, much like planets orbiting a star. What defines an element is the number of protons in its nucleus. 1 proton makes hydrogen, 6 protons make carbon, and this count is known as the atomic number. But for electricity, the real stars of the story are electrons, especially those in the outermost shell. Electrons closer to the nucleus are held tightly because the attraction between opposite charges is strongest at short distances, but electrons farther away feel a weaker pull, making them easier to remove. And these loosely held electrons are called valence electrons. The moment an external force nudges these valence electrons out of their shells, they begin jumping from atom to atom. And that collective movement of electrons is what we call electricity. Meaning electricity is not some invisible fluid rushing through wires, but trillions upon trillions of electrons gently drifting through a material under the right conditions, setting the foundation for everything from a glowing bulb to the internet itself. This is exactly why materials like copper are used for electrical wires, because each copper atom has a single valence electron that is very loosely bound, allowing electrons to move easily from one atom to the next, making copper an excellent conductor, while materials like plastic, rubber, glass, and wood hold their electrons tightly and do not allow free movement, which is why they are called insulators and are used for safety. Now, when these electrons start moving in an organized way, that movement is called electric current. And current simply tells us how many electrons are flowing through a wire every second, measured in amperes or amps, where 1 ampere means 1 coulomb of charge flowing per second, and 1 coulomb equals approximately 6.24 x 1018 electrons, an unimaginably large number. So even a small current involves an ocean of electrons moving together. If 1 ampere flows, that many electrons pass each second. If 2 amperes flow, double that number moves, and if half an amp flows, only half as many electrons pass through. But electrons don't move on their own just because a wire exists. There must be a driving force that pushes them, and that force is voltage. Voltage can be understood using simple analogies, like water pressure from a high tank pushing water through pipes, or a syringe creating suction when the plunger is pulled back. And in the same way, a battery creates an electrical pressure difference between its terminals. The negative terminal of a battery is packed with excess electrons, while the positive terminal lacks electrons, creating a natural urge for electrons to move from the negative side to the positive side when a path is provided. And this pressure difference between the two terminals is called electric potential difference, or simply voltage, measured in volts. A 1.5 volt battery means the pressure pushing electrons through the circuit is 1.5 volts, and without this pressure, electrons would never move no matter how good the conductor is. However, even when voltage pushes electrons through a conductor, their movement is never perfectly smooth, because as electrons drift through a wire, they constantly collide with atoms inside the material, losing energy in the form of heat. And this opposition to electron flow is called resistance. Every material has resistance. Copper has low resistance, aluminum has more, iron has even more. And resistance explains why wires heat up when current flows through them. This relationship between voltage, current, and resistance forms the backbone of electrical science, and although the formulas can be complex, the idea is simple. higher resistance slows current. Lower resistance allows it to flow more easily. Now imagine a basic circuit consisting of a battery, wires, and a bulb. Electrons leave the battery's negative terminal, move through the wire, pass through the bulb, and return to the positive terminal. And importantly, the number of electrons leaving the battery is exactly equal to the number returning, meaning electricity is a closed-loop system. Inside the bulb, there is a thin filament made of tungsten, a material chosen not because it conducts electricity easily, but because it resists it just enough. As electrons collide with tungsten atoms, the filament heats up to extremely high temperatures, glowing brightly and producing light, which is why a bulb lights up, converting electrical energy into light and heat energy. In a fan, electrical energy converts into mechanical motion, and in a heater or iron box, it converts into heat, proving that electricity itself doesn't change. Only the form of energy it becomes does. This simple principle powers nearly every machine humanity has ever built. When we scale this simple circuit up, replacing batteries with massive generators, the same process supplies electricity to entire cities, where generators create voltage by mechanical motion. Pushing electrons through long transmission lines into our homes, instantly powering devices the moment a switch is flipped. What feels like magic is actually electrons responding almost immediately to an electric field, even though individual electrons drift slowly, because the signal that pushes them travels nearly at the speed of light. Understanding this reveals something profound. Electricity is not mysterious or supernatural, but a beautifully organized dance of charged particles following the laws of nature. Once this foundation is clear, atoms, electrons, current, voltage, and resistance, electricity stops being intimidating and becomes logical, predictable, and powerful, giving us the ability to not just use technology, but truly understand it. And this understanding matters because the future of humanity is becoming even more electric, from renewable energy and electric vehicles to smart grids and artificial intelligence, all resting on the same simple principles hidden inside atoms. When people grasp these basics, they don't just switch on devices, they switch on curiosity, confidence, and control over the technology that shapes modern life. Which is exactly why learning how electricity works is not just useful knowledge, but essential awareness in a world that runs on invisible electrons every second of every day. Now, to truly appreciate how electricity feels instant, we need to clear one of the biggest myths people have, that electrons race through wires at lightning speed, because in reality, individual electrons drift very slowly, sometimes only a few millimeters per second. Yet the moment you flip a switch, the bulb lights up immediately. And this happens because electricity works more like pressure in a pipe than water itself moving fast. When a circuit is closed, an electric field is established almost instantly throughout the wire, pushing electrons everywhere at the same time, similar to how pressing one end of a long rod makes the other end move immediately, even though the atoms themselves barely shift. This is why electricity feels fast, even though electrons themselves are not sprinting through the wire. Understanding this also helps explain alternating current, or AC, which is what powers our homes, where electrons don't travel long distances at all, but vibrate back and forth in place, as the direction of voltage keeps changing many times per second, usually 50 or 60 times, depending on the country. This back-and-forth motion efficiently transfers energy without needing electrons to migrate across cities, making AC ideal for long-distance transmission. Direct current, or DC on the other hand, flows in a single direction and is used in batteries, phones, laptops, and electric vehicles, showing how both systems are based on the same principles but optimized for different needs. When you combine voltage-pushing electrons, current measuring their flow, and resistance controlling their speed, electricity becomes a predictable system rather than a mystery. And once people understand this, they stop fearing it and start respecting it, which is crucial for safety, innovation, and smarter energy use in everyday life. This understanding also explains why electrical safety rules exist, because resistance and current are not just technical terms. They directly affect the human body, which itself conducts electricity due to water and dissolved salts inside it. When voltage forces too much current through the body, It interferes with nerve signals, muscles, and the heart's natural rhythm, which is why even household electricity can be dangerous if resistance is lowered by wet skin or broken insulation. This is also why circuit breakers, fuses, and earthing systems are designed to instantly cut off current when it exceeds safe limits, protecting both humans and equipment. Zooming out further, the same simple electron movement powers entire nations through power grids, where electricity generated at power plants travels through transmission lines at high voltages to reduce energy loss, then gets stepped down safely before entering homes, proving that everything from a tiny LED to a massive city grid follows the same atomic rules. Once people truly understand electricity at this fundamental level, they don't just consume power, they begin to think differently about energy conservation, renewable sources, solar panels, wind turbines, and the future of a sustainable world. Electricity stops being an invisible service and becomes a living system we interact with every day. And this awareness transforms ordinary users into informed citizens of a fully electrified civilization, where knowledge itself becomes power, real power that lights homes, drives progress, and shapes the future. Once this foundation is clear, electricity stops feeling like something created only in power plants and starts revealing itself as a natural phenomenon that exists everywhere in the universe. Because long before humans learned to generate electricity, nature was already using it. In lightning storms that split the sky, in electric eels that hunt with shocks, and even inside the human brain, where tiny electrical signals travel between neurons to create thoughts, memories, and emotions. This realization connects everyday electricity to something far bigger, showing that wires and batteries are just tools we built to control a force that already existed. And when scientists understood this, they learned how to store, transform, and transport electrical energy efficiently. This is where devices like capacitors and inductors come into play, quietly working behind the scenes in chargers, power supplies, and electronics, storing energy temporarily, smoothing current, and protecting circuits from sudden surges. Even the simple act of charging a phone involves complex coordination between voltage regulation, current control, and resistance management, ensuring energy flows safely without overheating or damaging delicate components. The more devices we connect to electricity, the more important efficiency becomes, because wasted energy turns into heat, and heat is essentially lost power. Which is why modern engineering focuses heavily on minimizing resistance and optimizing current flow. Understanding these concepts also explains why thicker wires are used for high-power appliances. At this point, something interesting happens in the mind of the viewer, because electricity no longer feels like a school subject, but like a living story that explains everyday life. And this is where true understanding begins to lock in. Once people realize that every device around them, from a tiny earphone to a massive train, works by carefully controlling electrons, curiosity naturally increases and questions start forming on their own, like why devices have power ratings, why chargers get warm, why voltage standards differ across countries, and why some appliances consume more electricity than others. All of this comes back to power, which is simply the rate at which electrical energy is used, measured in watts, where power is the product of voltage and current, meaning higher voltage or higher current results in more energy being consumed per second. This explains why high-power devices like heaters, ovens, and air conditioners draw more current and require thicker wiring, while low-power devices like LED bulbs and phone chargers operate efficiently with much less energy. Understanding power also reveals why energy bills are measured in kilowatt hours, not watts, because electricity companies charge based on how long you use power, not just how powerful a device is. Suddenly, electricity bills stop feeling random and start making sense, empowering people to reduce waste, choose efficient appliances, and control costs intelligently. This shift from passive consumption to informed usage is one of the most valuable outcomes of understanding electricity. This deeper understanding also opens the door to one of the most fascinating realities of electricity: efficiency versus loss, because no electrical system is ever perfectly efficient. And some energy is always lost, mostly as heat due to resistance. This is why chargers feel warm, motors make noise, and power plants release massive amounts of heat into the environment. And engineers spend enormous effort trying to reduce these losses. Modern technologies like superconductors aim to eliminate resistance entirely by allowing electrons to flow without energy loss, under special conditions, hinting at a future where electricity could travel vast distances with near-perfect efficiency. Even today, improvements in materials, science, circuit design, and semiconductor technology have dramatically reduced losses compared to earlier generations, making modern electronics smaller, faster, and more powerful. Semiconductors like silicon occupy a special place between conductors and insulators, allowing engineers to precisely control electron flow, which is how transistors, the building blocks of all modern computers, work. Billions of these tiny switches operate every second inside smartphones and laptops, manipulating electrical signals to perform calculations, store memories, and display images, showing that electricity is not just energy, but logic itself. Once this clicks, it becomes clear that the digital world is simply electricity shaped by rules, patterns, and timing, and that every app, video, and algorithm ultimately traces back to electrons moving through carefully designed pathways. As this realization deepens, electricity begins to feel less like a human invention and more like a universal language that nature itself speaks fluently, because from the smallest transistor to the largest power grid, the same rules govern everything without exception. This is why engineers and scientists can predict electrical behavior so accurately, because electrons obey physical laws with absolute consistency, never getting tired, emotional, or confused. When a switch is flipped, an electric field instantly forms across the circuit, organizing electrons into motion, and this orchestration happens billions of times every second across the planet, silently powering hospitals, communication networks, satellites, and financial systems that modern civilization cannot survive without. Even inside our own bodies, electrical impulses regulate heartbeat rhythms, muscle contractions, and neural communication, meaning life itself depends on controlled electrical activity. Medical devices like pacemakers, MRI machines, and brain stimulators work precisely because scientists understand how electricity interacts with biological systems, further proving that electricity bridges the gap between technology and life. When people grasp this, electricity stops being dangerous magic and becomes a tool that demands respect and understanding rather than fear, which is why education about electricity is not optional in the modern world. It is survival knowledge. The more electrified society becomes, the more dangerous ignorance becomes, and the more valuable understanding becomes, turning basic electrical literacy into a form of personal power that protects, informs, and empowers individuals in everyday decisions. Looking ahead, the role of electricity is only going to expand because the future is not just digital, it is fully electric, with transportation, heating, cooling, manufacturing, and even agriculture increasingly shifting toward electrically driven systems. Electric vehicles are replacing combustion engines, not because electricity is new, but because we have finally learned how to store and manage it efficiently through advanced batteries and power electronics. Smart grids now balance electricity demand in real time, routing power intelligently to prevent overloads and blackouts, while renewable sources feed energy into the system from millions of decentralized points. This transformation rests entirely on the same foundational principles: current, voltage, resistance, and power, scaled up with precision and intelligence. As artificial intelligence grows, it relies on vast amounts of electricity to process data, meaning the intelligence of machines is directly tied to our ability to generate and distribute electrical energy sustainably. In this sense, electricity is no longer just supporting progress, it is defining it. And societies that understand and manage electricity well will lead the future, while those that waste or misuse it will fall behind. Once people see electricity this way, learning its basics stops feeling like a school requirement and starts feeling like preparation for the world that is already arriving.
At a deeper level, understanding electricity also changes how people think about responsibility, because every unit of energy used comes from somewhere and leaves an impact somewhere else. Power plants burn fuel, dams reshape rivers, solar panels require materials, and batteries depend on mining and recycling, meaning electricity is never truly free. It is borrowed from nature and must be repaid with care. When users understand how much energy their devices consume and why, they naturally become more conscious of efficiency, conservation, and sustainability, not because of fear, but because of awareness. Simple choices like using efficient lighting, unplugging idle devices, and optimizing usage times can collectively reduce massive energy waste, showing how small informed actions scale into global impact. This is where understanding electricity becomes not just technical knowledge, but ethical awareness, linking personal habits to planetary outcomes. When millions of people make smarter energy choices, the effect is stronger than any single technological breakthrough, proving that education is one of the most powerful energy-saving tools humanity has. Electricity, once understood, teaches us that progress and responsibility must grow together, or neither will last. And finally, when all these layers come together, electricity reveals its most powerful lesson: that complex systems are built on simple truths repeated perfectly at scale. At its core, electricity is just electrons responding to forces. Yet from that simplicity emerges the modern world, with its cities, networks, knowledge, and connections. This mirrors human potential itself, where small, consistent actions, guided by understanding, create extraordinary outcomes over time. When people truly understand electricity, they don't just use technology better, they think differently about systems, cause and effect, efficiency, and balance. This mindset carries beyond wires and circuits into problem-solving, innovation, and decision-making across all areas of life. Electricity becomes more than a topic. It becomes a way of seeing the world, where nothing is random, everything follows rules, and understanding those rules unlocks power. And that is why learning how electricity works is not just about lights turning on, but about turning on curiosity, confidence, and control in a world that runs on invisible forces, reminding us that the future belongs not to those who simply consume power, but to those who understand it. When this understanding fully settles in, something subtle but powerful happens. The fear of complexity disappears, because electricity proves that even the most advanced systems in the world are built from simple principles repeated billions of times with discipline and precision. This is why learning electricity becomes a confidence booster, especially for young minds. Because once someone understands how electrons move, how voltage pushes, and how resistance controls, they realize that technology is not reserved for geniuses or experts, but is accessible to anyone willing to understand the basics. This mindset is exactly what turns viewers into learners, learners into creators, and creators into innovators, which is how every major technological leap in history has happened, from Edison's bulbs to Tesla's AC systems, from microchips to satellites. Progress always started with someone who understood electricity deeply enough to imagine new possibilities. Even today, startups building electric vehicles, renewable grids, robotics, and AI systems all rely on engineers who see electricity not as abstract math, but as behavior they can shape and control. Once viewers reach this level of clarity, they don't just watch content, they trust it. And that trust is what builds long-term audiences, because people naturally return to sources that make them feel smarter, calmer, and more capable after every video. So when everything finally comes together, electricity stops being just wires, switches, and devices, and becomes a mirror of how the modern world actually works. Simple rules repeated endlessly, creating complexity, power, and progress. From tiny electrons moving between atoms to massive power grids lighting entire cities, the same principles quietly run everything, reminding us that understanding basics is what unlocks control, confidence, and creativity. This is where learning electricity is not about memorizing formulas, but about seeing the invisible systems shaping daily life, from the moment an alarm rings in the morning to the second a screen lights up at night. Once people truly grasp how current flows, how voltage pushes, how resistance shapes behavior, and how energy transforms from one form to another, technology stops feeling overwhelming and starts feeling approachable. Curiosity replaces fear, logic replaces confusion, and awareness replaces blind usage. And in a world racing toward electric vehicles, renewable energy, smart homes, and intelligent machines. This understanding becomes more than knowledge. It becomes preparedness for the future. Electricity teaches us that progress belongs to those who learn how things work, not just how to use them, and that the real power is not in the socket on the wall, but in the mind that understands what flows through it. Once that switch turns on, it never really turns off, because the world itself starts making sense in a deeper, calmer, and more connected way.